Okay, so for today, today is going to be a problem session for properties of logarithms. So hopefully, for the two of you that are here, as well as anyone else that shows up, you have already seen the properties of logarithms lecture video that I have posted in my math lab. And yeah, so primarily I'm just going to go over problems I didn't talk about in the video. So this is in reference to the section here, which is due on the 6th, which is, I believe, Friday. So please make sure you get that done. So I suppose, do either of you in here have any specific problems you'd like me to do? Anything in particular? If not, I'll just work problems just kind of arbitrarily. Did either of you already finish the homework by chance? If so, you know, you don't have to be here if you've already finished the homework. But, yeah, I can go over the graphs, that's fine. Let me just look for them right fast. Okay, and if you know the number, you can go ahead and tell me the number. I'll find them here in a bit, though. The graphs. Shouldn't take too long. Oh, 1 second. I'm not too sure which graph problem you're referring to. If you have a specific number that you can reference me to, I don't see any graphs in this section, unless I'm in the wrong section. Hope not. Yeah, properties of logs. Yeah, I'm not too sure about the graphs. Yeah, I think this is a section solely based off of just logarithmic problems, just algebraic, solving problems algebraically. Oh, that's okay. Let me see what I haven't talked about, and I'll talk about those in the homework. Okay, so I'm just going to compare the two and go through them one by one. So the, just as a warm up, the log base A of 1, with the log of 1, the log of 1 is always 0, and one way to motivate this is by rewriting this in a calculator-friendly form. So I talked about this in the video. There's this calculator-friendly equivalent statement you can write, and that's this one right here. Now, obviously, you can't write this in the calculator in its entirety because there's an A, there's a symbol. But log of 1, you can put that in the calculator. Sorry about the sneeze. Okay, it went away. Sorry about that. Okay, so log of 1, you could put log of 1 in the calculator and you would get 0 over log of A. But it doesn't even matter what log of A is because 0 divided by anything is just 0. So that's kind of the motivation behind some of these first few. So what I'm emphasizing here is this way of rewriting a problem from this form to this form right here, the calculator-friendly form. This is going to be really helpful. And again, I'm hoping I've made quite a few references to this in the video, so just to be consistent. But let's keep going with other problems. Where am I at? Okay, cool. So let's keep going. So I do talk about this one in the video, so I'm going to skip problem 2 here. So I talk about it. You can see it's part 1 over here. And then this is a definition. This is a straight definition. In fact, you can find it right up here, just right there. So we can fill in that one right fast. So which one is that? It's this one. So just a definition, just to make sure you know your formulas. And same thing with the quotient rule. Again, it's just spacing it out term by term. Pretty straightforward stuff. And this is another one. This is the power rule, which you will see right here. So again, just another definition. Again, you might already know all of this, but just to go through the problems one by one, there's only 25, so it might not take some of you too long to go through some of these problems. This right here, I covered this problem in part 2. So you can see a similar problem in part 2. And so this is probably 85. So again, that part's in the video, so I'll skip it. I'll talk about this problem as well. Just to explain this one, the ln and the e cancel. So this one's really easy. And then let's say I covered quite a few of the problems from the homework here. So here I did a problem just like this one for number 4. But again, just to kind of emphasize this idea. And I like to use parentheses. I'll sometimes put parentheses around the numbers the log is evaluating to sort of separate it from the subscript. But this is the product rule. So you can use the product rule whenever you're adding 2 logarithms together with the same base. And so the product in question is just 3 times 4, which is log base 12 of, well, 12. And then guess what? We can evaluate this in the calculator. This is log of 12 divided by log of 12 using the calculator-friendly version. And if you threw that in your calculator or you saw that it's just something divided by itself, you get 1. So there's another example of that, 1. So again, you might be able to get through this problem or this homework section fairly quickly. But it does identify the types of formulas at play that correspond to the logarithms. And also with this one, again, this one I talked about in the video. This one's part 5 over there. I'll just do another one. Since you are subtracting logs here, you don't use the product rule, you use the quotient rule. So use the quotient rule right up here on the top left. So it says you can take a difference and write it as, well, guess what? A quotient. And the 40 goes on top and the 8 goes on the bottom. So 40 divided by 8, I believe that's just 5. And you can write it in the calculator-friendly version to figure out that final answer is 1. This problem, as I probably explained in the video, you start with evaluating the exponent, so the difference of the logs. And I'll just kind of reserve, and really I'll reserve that process to the lecture video. So yeah, as you can see, example 10 here corresponds to part 6 from example 1 of the notes. So let's go ahead and see what else there is. Okay, so I talked about this one as well. So you might notice that this is part 1 from example 2. Just to give another example of this. This is well, it even tells us write the expression as a sum or difference of logarithms. So here we are utilizing the fact that there is a product, and we're going to apply the product rule. Which means every part of the product gets its own logarithm separated by plus signs. And if you try to type this in as your final answer, it's going to say it's wrong, because this part right here can actually be simplified. Log base 6 of 1296, I'm pretty sure that could be simplified. So something I hopefully mentioned in my lecture video is that if you have a logarithm that has just numbers in it, you can attempt to simplify it if you can. Because log base 6 of 1296 is equal to log of 1296 divided by log of 6. And let's see what that looks like in the calculator. Log of 1296 divided by log of 6. And I get 4. So it does simplify very nicely. So this is scratch work off to the side. And now we can simplify this as 4 plus log base 6 of x. And we're not solving for anything. We're not trying to get an x by itself. So we can just conclude with 4 plus log base 6 of x. And again, the parentheses are optional. I recommend putting them. But if you didn't put the parentheses around the x, that'd be fine. So again, this should be fairly, this should pretty much correspond to what I have in the lecture. So it looks like I don't have this one. So I'll go ahead and do this problem. And again, I'm putting parentheses around the z raised to the 9th, just habit of mine. And so to simplify this, you might look and think, all right, well, I don't see any products and I don't see any quotients, but I do see a power. There's a power. And remember, we have a power rule, which tells us we can bring the 9 to the very front. And really, that's all you can do. We've applied all the product, quotient, and power situations within the logarithm. So we cannot simplify this any further. So that's just a power rule. And I normally illustrate it by that characterization in red. You might notice that this problem is exactly this problem over here. They might give a variation that I might want to look at. Okay, maybe that's another problem. All right, so I did that exact problem already in the notes in part 4. So I'm going to skip that one. I'll go ahead and talk about this one, because this one may or may not be tricky. So what we have here is a natural log of a quotient, which means we would use the quotient rule. So the quotient rule tells us it's natural log of the numerator, and the quotient rule tells us we have to use a minus sign for the natural log of the denominator. So notice the numerator goes into the first one, the denominator goes into the second one. And they both get their own natural log with a difference, a minus sign. And there's one more way we can simplify this, because obviously you can't plug either of these into the calculator because there are x's. X's are symbols, so you can't put those in the calculator. However, natural log and e, they both cancel when they are next to each other without any interference. So really, what this comes out to be is natural log of x minus that x that was left over. And that is our final answer. So this is not one that I do in the notes, so that might be helpful. So notice we're more than halfway done with the homework here. So you might be able to get this one done fairly quickly. Okay, I also didn't do this one, so I'm going to talk about 15 as well. And normally they will put parentheses whenever the logarithm is evaluating something that has a little bit more extended of a form. So u to the 9, and then they have the v to the 4th. So that's a lot of stuff going on. They'll put parentheses around it just to imply that all of this is within the logarithm. But so here they want us to write the following expression as a sum and or difference. So what you have to realize is first that there is a product here. There's a product. I mean, there's also exponents. So you might think use the exponential rule. But what exponent would you bring to the front? The 9 or the 4? And the answer is it's not very easy to determine that. You're not taking the logarithm of an exponent. You're taking the logarithm of a product of two exponents. So that's when you have to realize, all right, which rule do I use first? Am I using the exponential rule or the product rule? And you're using the product rule because this is a product first, and then within the product, there are two exponents. So the product rule, and sometimes Sometimes I will, above the equal sign, put a PR or some sort of label to emphasize that this is a product rule, a quotient rule, or an exponential rule. I'm using the product rule here. U to the ninth power is the first part of the product. The product rule tells us to add the second part, or the logarithm of the second part of the product. Just like that. So notice each part of the product now gets its own logarithm, and now they are separated by a plus sign. But we're not done, because they have this additional condition here that says express powers as factors. And what that means is if you have any exponents, you need to bring them to the front. So you'd bring 9 to the front of that logarithm, and you would bring 4 to the front of this logarithm. This is two applications of the exponential rule. So I'll put ER. So this is 9 log base b of u plus 4 log base b of v. And that is your final answer right there. So this is when it starts getting into nested rules or rules within rules. So there's a product rule, but then within the product rule, there's an exponential rule. So I guess besides for that, let's go ahead and move on. I talk about this problem almost exactly for part 5. So I'll go ahead and skip that. Let's see. I did not do this problem, so I'll go ahead and talk about this problem as well. So again, the problem wants us to write as a sum and or difference of logarithms. So first we need to figure out, what are we taking the logarithm of? Is it a product, a quotient, or an exponent? Now, I see an exponent in there, and I see a quotient. So the question is, which one do I use first? Are we taking the logarithm of a quotient with exponents inside of it, or are we taking the logarithm of an exponent with quotients inside of it? And the answer is, we're taking the logarithm of a quotient. So if we assumed otherwise, if we assumed we were taking the logarithm of an exponent, well, we would not be able to bring the 12 to the front, that exponent of 12 to the front, because that 12 is not the exponent of x minus 8 in the denominator. So this is a quotient rule, because we are evaluating the log of a quotient first. So this is log base 6 of the numerator, x to the 12, minus log base 6 of the denominator, x minus 8. But it also says, as I have highlighted, express powers as factors, which means if you have any exponents, as we do, then we need to bring them to the front. So we are now applying the exponential rule, which is now 12 log base 6 of x minus log base 6 of x minus 8. And this would be our final answer here. So this would be our final answer. So again, this is another problem I did not talk about in the video, it doesn't seem like, so this is how to do one like this, number 17 for the homework. Okay, we also don't seem to have an example of number 18. So I'll go ahead and talk about this one as well. This one's kind of similar to part 6, not entirely so, but it's a little bit similar to part 6. If you look at part 6 from example 2, you might see some overlapping themes. But the first thing we ask ourselves is, all right, so we're trying to express this as a sum or difference again. So we think about it as, are we taking the logarithm of a product, quotient, or an exponent first? And so I see a product in the numerator, I see an exponent in the denominator, and I also see a quotient. So we have all three rules at play here. And we need to figure out which one do we use first. Are we evaluating a product first? So is that whole expression just a giant product of two things? Or is it a quotient, or is it an exponent? And the answer, it's a quotient. Because within the quotient, the numerator within the quotient has a product, and the denominator within the quotient has an exponent. So really, this is a quotient rule first, which means we evaluate the logarithm of the numerator. And then the quotient rule tells us to subtract the logarithm of the denominator. Just like that. That's the quotient rule. And now, within the quotient rule, we now have smaller individual logarithms for which we need to evaluate. So we'll start with the first logarithm. The first logarithm, are we evaluating a product, quotient, or an exponent? That looks like a product. That looks like a product rule, because it's x times x plus 7. For the x plus 6 raised to the 15th, that looks like an exponential rule, because there, of course, is an exponent. There's the 15, which we can bring to the front of that corresponding logarithm. And so we can conclude, so the product rule tells us that we have log of x plus log of x plus 7. And then finally, minus 15, because we bring the 15 to the front, log of x plus 6. And that would be our answer, because there's no further way to simplify any of those expressions any further. Let's see, did I write something down wrong? X plus, oh, where did I get a 6 from? I don't know why I wrote 6. For any of you who noticed that and just watched me keep messing up, sorry about that. I don't know why I wrote a 6. That should definitely be a 4. I just wrote the problem down wrong, my fault. So what's that, +4? And then down at the bottom, +4. I don't know why I do that sometimes. Oh well. Okay, so it should be +4. All right, cool. Okay. All right, so let's keep going. We only have 7 or so more problems to go, or 6. So I talked about this problem here. So this one is definitely like part 6 down here. So I'm going to skip that. The x is greater than 2. You can ignore that. That's just a formality. It doesn't really, it's just a domain thing. You don't have to worry about it though. So we'll skip number 19 because that's part 6 and example 2 here. So then we'll move on to the other direction. We have a collection of logarithms being added or subtracted, and we want to combine them as a single logarithm. So that's the goal here now. So this corresponds to the collection of problems on page 85 of the class notes. And you might notice that, in fact, there might be a chance that all 6 of these correspond to the remaining 6 or so problems. So let's see what follows. So this one right here, you may notice, corresponds to part 1. So I'm going to skip that one. This one corresponds to part 2. This one actually corresponds to part 5. As you can see, there is a difference of squares. In fact, I'll just work this one out. So they want us to write this as a single logarithm. So that means that we're going in the reverse direction that we've been going in. But the first thing we have to do before we can start combining logs together is we need to write factors as powers. Remember, we were taking exponents and putting them in front of the logarithm. But in order to combine logarithms, we need to go backwards. We need to write factors as powers and put them back. We have to do this before we can combine logarithms together. So as soon as we apply the exponential rule, now we can combine the logarithms together using, well, whatever rule corresponds to a subtraction of logs, which is the quotient rule. Here we use the exponential rule. And going to the next step, this is going to be the quotient rule, because that's what corresponds to the subtraction of logarithms. So now we can combine this as one logarithm, where we have x squared minus 9 in the numerator, and x plus 3 to the 5th power in the denominator. Now we're not done. If you tried to type this answer in, it's going to say, in fact, let's just see what it says. So this won't be the right answer. All right. I was hoping it would say your answer is correct, but not simplified, but it doesn't give any sort of indication here. So this is So you might, oh, well, now I realize why, but a plus 9. Well, it's definitely going to complain about this, and it's going to say that the answer is like x minus 3 over x plus 3 to the fourth power. So the reason why it's this is because the numerator can actually be factored as a difference of two squares. So x squared minus 9 is x plus 3, x minus 3. All of this over x plus 3 to the fifth power. And then there's the cancellation here. So the x plus 3 will cancel with one of these x plus 3s, leaving just 4 x plus 3s, which is why the answer ends up being as it's stated there. And that would be writing a bunch of logs as a single logarithm. So we'll go ahead and move on to the final parts. So this part here is almost exactly part 6 down here. So I'll go ahead and move past that one, see what 24 says. So go ahead and do this one. So for this problem here, we want to take this, well, what seems to be a difference of several logs and combine them as a single log. And really the first thing we have to do, we want to make sure that all factors are rewritten as powers. So notice there's a factor right here. There's a 3 in the front. We want to write that as a power, because we have to get all of those factors out of the way before we can start combining logarithms together. It's plus 7 to the third power, and then everything else carries over. And so now we can start combining logs. So how do we combine 3 logs together? Well, we have to combine 2 logarithms together first, and then combine the third one last. So we're going to go ahead and combine these two together. And those two, it's 2 logarithms separated by a minus sign. So this is going to be the quotient rule, which means we can write this as 1 logarithm with x plus 7 to the third power in the numerator and x minus 8 in the denominator. So that's combining the first 2 logarithms together. And now to combine these 2 logarithms together, it's the same idea. But we're going to rely on a little bit of algebra. You can combine these together as 1 logarithm. Which instantly sends the x minus 14 to the denominator, because we're dividing a fraction by a number, and that number is going to end up in the denominator. So this will be our final answer here, because we have now combined all of the corresponding logarithms as a single logarithm. So that's another one that I haven't covered. This one is actually very similar, or fairly similar to part 4. It just seems like they took the quadratic part here and already did a step for you, from what it seems like. And as we keep going, we hit the last problem in the homework, which is actually covered in my notes for example 4 here. In fact, you can see it's almost the exact same problem, except instead of x to the 6th, it's x squared. So really, I'm just going to leave it there. That covers every homework problem. And hopefully you don't have too many issues with this homework. Something to keep in mind before I conclude here. It might be good to go ahead and get this homework out of the way, because notice that upon getting this homework out of the way, you get a nice little break until the next homework assignment. So notice the 13th is when the next homework is due. So the sooner you get this one done, the sooner you can take a little bit of a break from this class for a few days, and that's always nice. So I suppose besides for that, if you have any questions, you can go ahead and ask me. Other than that, that's all I have for today. Have a good day.